There is a planet next door that is almost exactly the same size as ours. It is made of the same materials, formed at the same time out of the same cloud of dust. It has nearly the same mass, nearly the same density, nearly the same gravity. If you compared the two on paper without labels, you would struggle to tell them apart. On its surface, lead would melt into a puddle within seconds. The temperature there is around 465 degrees, not in a desert at noon, everywhere, at the poles, at midnight. It never varies, and it never cools. The air presses down with 92 times the weight of our atmosphere, which is what you would feel 900 meters beneath the ocean. The clouds are not water. They are droplets of sulfuric acid, and they never reach the ground because it is far too hot for anything to fall that far without evaporating. Every machine we have ever landed there has died within hours, most within minutes. And yet this world may once have had oceans, possibly for billions of years, possibly while life was getting started here. Two planets, the same size, the same distance apart in the same solar system, born together. One became the only place we know of where anything lives. The other became the most hostile surface in the solar system. Tonight, we go and find out what happened. If you find calm in the strange histories of other worlds, consider subscribing to the channel. Let the story of our nearest neighbor carry your mind somewhere restful as we drift together tonight. Welcome aboard, astronaut. Tonight, we drift through the cosmos. We do not go far. Venus is the closest planet to us, and at its nearest approach, it comes within about 40 million kilometers, closer than anything else ever gets. You have almost certainly seen it. It is the brightest object in our night sky after the moon, bright enough to cast faint shadows in a genuinely dark place, and bright enough that people regularly report it as something unexplained. It appears low in the west after sunset, or low in the east before dawn, which is why it has been called both the evening star and the morning star for as long as anyone has kept records. As we approach, it grows into a perfect, featureless disk, pale yellow-white, entirely smooth, with no markings whatsoever. That blankness is the clouds. They cover the entire planet without gaps, permanently. For most of human history, nobody had any idea what lay beneath them, and the guesses were extraordinary. Swamps, jungles, oceans, a hot, wet, prehistoric version of Earth. Tonight, we will go through those clouds and find out what is actually down there. We will trace how a planet almost identical to ours ended up like this, follow the evidence of an ocean that is no longer present, and learn why the same carbon that makes Venus unbearable is sitting quietly in the rocks beneath your feet. Settle in. Let your breathing slow. Nothing about tonight is urgent, though the story underneath it is. Let us begin with how similar they are. Venus has a diameter of about 12,100 kilometers. Earth is 12,700. That is a difference of 5%. Venus has 82% of Earth's mass. Its surface gravity is about 90% of ours, which means you would weigh very slightly less standing there and would barely notice the difference. Its density is nearly identical to ours, which tells us the internal structure is similar. An iron core, a rocky mantle, a solid crust. Same ingredients, same proportions. Both planets formed at the same time, 4.5 billion years ago, from the same disk of material orbiting the young sun. They accumulated from the same population of rocks and were struck by the same population of comets and asteroids. In terms of orbit, Venus sits about 72% of our distance from the Sun. It receives roughly 1.9 times as much sunlight as we do. That is the entire difference in starting conditions, slightly closer, slightly smaller. Everything else was essentially the same. For a long time, this similarity encouraged optimism. Venus was widely imagined as a younger, warmer Earth. The clouds suggested water. The extra sunlight suggested a tropical world. Serious scientists proposed global oceans and lush vegetation, and science fiction ran with it enthusiastically for decades. Then, in the 1960s, we sent something to look. But that's not all, because long before any spacecraft, Venus had already done more for science than almost any other object in the sky. In 1610, Galileo turned his telescope on it and noticed something nobody had ever seen. Venus had phases, exactly as the moon does. Sometimes a thin crescent, sometimes half-lit, sometimes almost a full disk. That observation was devastating to the old model of the heavens. If Venus orbited the Earth on a path that always kept it between us and the Sun, as the ancient system required, it could never appear fully illuminated. A full Venus is only possible if Venus passes behind the Sun. A single set of observations, made with a crude instrument, ruled out a cosmology that had stood for 14 centuries. Venus performed a second service 150 years later. Occasionally, in rare pairs separated by long gaps, Venus passes directly across the face of the Sun. Astronomers realized that if observers in widely separated parts of the world timed such a transit precisely, the small differences between their measurements could be used to calculate the distance from Earth to the Sun. Nobody knew that distance. The relative spacing of the planets was well understood, but the absolute scale of the solar system was unknown. So, for the transits of 1761 and 1769, hundreds of observers were dispatched across the globe at considerable expense and personal risk. One famous voyage carried astronomers to the Pacific specifically for the purpose. It was arguably the first large international scientific collaboration in history. And it worked. The result came within a few percent of the value we use today. Everything we know about distance in space is built on a foundation that Venus provided by walking in front of the Sun. Now, let's go deeper into what we found. The first successful mission to another planet flew past Venus in 1962, carrying a radiometer to measure the temperature beneath the clouds. The result was not what anyone hoped. The surface was extraordinarily hot. Later measurements refined the number to around 465 degrees. To put that in context, it is hotter than a domestic oven at maximum. It is hot enough to melt lead, tin, and zinc. It is hot enough that rock at the surface glows faintly in the infrared. And it is remarkably uniform. There is no meaningful difference between the equator and the poles, or between day and night. The thick atmosphere circulates heat so efficiently that the entire planet sits at the same temperature always. The pressure is equally brutal, 92 times Earth's atmospheric pressure at the surface. That is what a submarine would experience 900 meters down. At that pressure and temperature, carbon dioxide stops behaving like a normal gas. It becomes a supercritical fluid, something between a gas and a liquid, dense enough that the atmosphere near the ground behaves almost like a warm sea. The composition is simple and unforgiving. 96.5% carbon dioxide, 3.5% nitrogen, and small quantities of sulfur dioxide and other compounds. The clouds, which sit between about 45 and 70 kilometers up, are droplets of concentrated sulfuric acid. They reflect around 3/4 of the sunlight arriving, which is exactly why Venus looks so brilliantly bright from Earth. But what happens when you ask why it is so hot? The obvious answer is that Venus is closer to the Sun. The obvious answer is wrong. Mercury is far closer, less than half Venus's distance. Mercury receives about 6.5 times more sunlight per square meter. And Venus is hotter, considerably hotter. Mercury's surface reaches around 430 degrees at its hottest point and drops to nearly 180 below zero at night because it has no atmosphere to hold the heat. Venus stays at 465 everywhere, always. There is a second surprise. Because those bright clouds reflect 3/4 of the arriving sunlight straight back into space, Venus actually absorbs less solar energy than Earth does. Less energy arriving, and a far hotter surface. The explanation is the greenhouse effect, operating at a scale nothing else in the solar system approaches. Sunlight that does penetrate the clouds warms the ground. The warm ground radiates that energy back upward as infrared. And carbon dioxide is extremely effective at absorbing infrared radiation. So the heat cannot leave. It is absorbed by the atmosphere, re-radiated in all directions, absorbed again, and re-radiated again, with only a small fraction escaping at each stage. Earth has a greenhouse effect too, and we depend on it. Without any greenhouse gases at all, our average temperature would be around 18 degrees below zero, and the oceans would freeze. Our atmosphere raises that by about 33 degrees to something comfortable. On Venus, the same mechanism raises the temperature by more than 500 degrees. Same physics, same molecule, a completely different outcome because of how much of it there is. And yet, there's more to this story, because the question becomes where all that carbon dioxide came from. And the answer is genuinely startling, because Earth has just as much of it. We do not usually think of our planet as carbon-rich, but it is. The difference is where the carbon is kept. On Earth, the overwhelming majority of carbon is not in the air. It is locked inside rock. Limestone, chalk, marble, and the vast carbonate deposits on the ocean floor are all essentially stored carbon dioxide bound into mineral form. If you could somehow release all the carbon held in Earth's carbonate rocks back into the atmosphere, our air would become roughly as thick and as carbon-rich as Venus's. Estimates put the resulting pressure in the same range, several dozen atmospheres of carbon dioxide. Read that again, because it reframes everything. Earth is not carbon poor compared with Venus. Earth has a comparable amount. Ours is simply filed away in the ground, and theirs is in the sky. So the real question is not why Venus has so much carbon dioxide in its atmosphere. The question is why Earth does not. What is our planet doing that Venus is not? The answer involves water, rock, and a slow cycle that has been running here for billions of years. The journey continues to that cycle because it is the heart of the whole story. On Earth, carbon dioxide dissolves into rainwater, forming a weak acid. That mildly acidic rain falls on exposed rock and slowly breaks it down, releasing dissolved minerals which are carried by rivers into the sea. In the ocean, those minerals combine with dissolved carbon dioxide and precipitate out as carbonate. Marine organisms accelerate this enormously by building shells and skeletons from it. When they die, the material settles to the sea floor and accumulates as sediment, then as rock. Over millions of years, plate tectonics carries that sea floor down into the mantle at subduction zones. Some of the carbon is eventually returned to the atmosphere through volcanoes, completing the loop. The remarkable part is that the whole system self-regulates. If the planet warms, there is more evaporation and more rainfall, which speeds up the weathering of rock, which pulls carbon dioxide out of the air faster, which cools the planet again. If the planet cools, weathering slows. Volcanoes keep adding carbon dioxide, and the atmosphere warms back up. It is a thermostat. It operates slowly over hundreds of thousands of years, but it has kept Earth's temperature within a livable band for most of our history, even as the sun has steadily brightened. The critical requirement is liquid water. Without rain, there is no weathering. Without oceans, there is nowhere for the carbonate to form and settle. Venus has no liquid water anywhere, which means Venus has no thermostat. Volcanoes have been adding carbon dioxide to its atmosphere for 4.5 billion years, and nothing has ever taken any of it out. Now, let's go deeper into what happened to the water. Because there is direct evidence that Venus used to have some, and quite a lot of it. The evidence comes from hydrogen. Most hydrogen atoms have a single proton in the nucleus. A small fraction have a proton and a neutron, making them roughly twice as heavy. That heavier version is called deuterium, and both types occur naturally in water. Here is why the ratio matters. When water molecules are broken apart high in an atmosphere, the resulting hydrogen can escape into space because it is extremely light. Deuterium is twice as heavy, so it escapes more slowly. Over long periods, a planet losing water to space becomes progressively enriched in deuterium. The light hydrogen leaves, and the heavy hydrogen lingers. Venus's atmosphere has a deuterium ratio roughly 150 times higher than Earth's. That is an enormous enrichment, and there is no plausible way to produce it except by losing an enormous quantity of water over a very long time. The measurement does not tell us exactly how much water there was. Estimates range from a shallow global layer a few meters deep to something comparable to a substantial ocean. But the direction is unambiguous. Venus had water. Venus lost it. And the water did not simply evaporate into space in one piece. It was taken apart, molecule by molecule, in the upper atmosphere, and the hydrogen was carried away by the solar wind. The oxygen left behind mostly ended up bound into rocks and into the sulfur compounds we now see. Now, let's go deeper, because that loss has not stopped, and we have watched it happening. Venus has no global magnetic field. Earth generates one in its liquid outer core, where circulating molten iron acts as a dynamo. Venus has a similar core, and it may well still be partly liquid, but it appears not to be circulating. The suspected reason connects back to plate tectonics. Earth's moving crust carries heat out of the interior efficiently, which keeps the core cooling and the circulation running. Venus, with a single rigid shell, cannot shed heat the same way. Its interior stays hot. The temperature difference across the core is too small to drive convection, and the dynamo never gets going. Without an internal field, the solar wind reaches Venus directly. It strikes the upper atmosphere, and the interaction generates a weak field that drapes around the planet like fabric over a stone. A spacecraft in orbit around Venus spent 8 years measuring what leaves through that region, and the result was striking. It detected a steady stream of ions escaping into space behind the planet. And when the composition was measured, the ratio was almost exactly 2 hydrogen atoms for every 1 oxygen atom. 2 to 1. The precise ratio of the atoms in a water molecule. Venus is still losing water today, in real time, atom by atom, into the solar wind. We have measured the rate. There is very little left to lose. The atmosphere holds only traces of water vapor now, a tiny fraction of what Earth's air carries. But the process that emptied the planet is not a historical event. It is ongoing, and it will continue for as long as anything remains. But what happens when we ask whether that water was ever an ocean? This is where the science is genuinely unsettled, and it is worth being honest about it. One picture is optimistic and has been influential. In this version, early Venus received less sunlight because the young sun was around 30% dimmer. That reduced brightness may have been enough for water to condense and remain liquid. Climate simulations along these lines suggest Venus could have held shallow oceans and moderate temperatures for a long stretch, possibly 2 or 3 billion years. In that picture, Venus was habitable while life was establishing itself on Earth, and only lost its oceans relatively recently in geological terms, as the brightening sun finally pushed it over the edge. It is a compelling story, and it makes Venus feel like a tragedy rather than a curiosity. But there is a serious challenge to it. Other modeling work argues that Venus may never have cooled enough for water to condense in the first place. In that picture, the young planet stayed hot after formation. its water remained permanently as vapor, and thick clouds formed on the night side in a way that trapped heat rather than reflecting it. The oceans never got the chance to form at all. If that is right, Venus was never a second Earth. It was born hot and stayed hot, and the water we know it lost was always in the air. Both pictures explain the deuterium evidence equally well. Distinguishing them requires measurements we do not yet have, particularly detailed chemistry of the deep atmosphere and analysis of the oldest surviving terrain. That is one reason several new missions are being sent. And yet, there's more to this story. So let us describe the runaway itself, because it is a genuinely important process. Whichever starting point is correct, the mechanism that locked Venus into its current state works the same way, and it is worth understanding because it applies elsewhere. Water vapor is a powerful greenhouse gas. That single fact drives everything. Suppose a planet with oceans warms slightly. Warmer oceans evaporate more readily, putting more water vapor into the air. More water vapor traps more heat, which warms the surface further, which drives more evaporation. This loop is self-limiting. The extra vapor condenses into clouds, rains out, and the system settles. The loop stops settling. Evaporation outpaces condensation, and the entire ocean is gradually lifted into the atmosphere as vapor. Once water vapor reaches the upper atmosphere in quantity, the second stage begins. Ultraviolet light from the sun breaks the molecules apart into hydrogen and oxygen. The hydrogen, being the lightest element, escapes to space and is gone permanently. This is the irreversible step. Evaporation alone could be undone by cooling. Losing the hydrogen cannot. Each molecule that breaks apart in the upper atmosphere is one molecule of water the planet will never have again. Give it enough time, and the water is simply gone. And with the water gone, the carbon thermostat stops working. Carbon dioxide accumulates without limit, and the surface settles into permanent, extreme heat. Astronomers call this a runaway greenhouse, and Venus is the only example we can study directly. The journey continues to a detail that has nothing to do with heat and is strange in its own right. Venus spins the wrong way. Every other planet in the solar system rotates in the same direction it orbits, which is the direction the original disk of material was turning. Venus rotates backwards. On its surface, the sun rises in the west and sets in the east. It is also extraordinarily slow. A single rotation takes 243 Earth days. Its year takes 225 days. So a day on Venus is longer than its year. The planet completes an orbit before it manages to turn around once. Because the rotation and orbit run in opposite directions, the interval from one sunrise to the next works out to about 117 Earth days, roughly 2 months of continuous daylight, then 2 months of night. Though the thick atmosphere means the difference in temperature between them is essentially nothing. How it ended up like this is not settled. One explanation is a massive collision early in its history that flipped or reversed it. Another is more gradual and, to me, more interesting. Venus has an extremely thick atmosphere, and both the sun's gravity and solar heating exert torques on it. Over billions of years, those forces may have slowed the original rotation to a standstill and then pushed it slowly backwards. If that is right, Venus's strange spin was not caused by a catastrophe. It was worn into place, gradually, by sunlight and air. Now, let's go deeper. Into the atmosphere, which does something the planet does not. The solid body of Venus turns once every 243 days. The upper atmosphere circles the entire planet in about 4. The clouds are moving around Venus roughly 60 times faster than the ground beneath them. Wind speeds at cloud level reach about 360 kilometers per hour, comparable to the strongest jet streams on Earth, sustained permanently across the whole planet. Astronomers call this superrotation, and it is one of the enduring puzzles of planetary science. Something must continuously transfer momentum upward from the slow surface to the fast atmosphere, and the details are still being worked out. Thermal tides driven by solar heating appear to play a major role. Down at the surface, the situation reverses completely. Wind speeds there are only a few kilometers per hour, a slow walk. But that gentle breeze is deceptive. The air near the ground is so dense, about 50 times denser than ours, that even a slow current carries enormous force. Moving through it would feel less like wind and more like standing in a river. Images returned from the surface confirm this. They show small rocks and fine material that have clearly been moved and sorted, and evidence of wind streaks across the plains. So Venus has weather, ferocious weather high up, and a slow, heavy, relentless flow at the bottom, pushing patiently at the stones. But what happens when we look at the ground itself? Radar can see through the clouds, and in the early 90s, a spacecraft mapped 98% of the surface in detail. What it found does not look like Earth, and it does not look like the Moon either. By smooth volcanic plains that function something like continents, extensive lava channels, and mountain ranges pushed up by compression. There are also features found nowhere else. Large circular structures, some hundreds of kilometers across, appear to have been created by plumes of hot material rising from the interior and pushing the crust upward before collapsing back down. But the most informative discovery was about craters. Venus has roughly 1,000 impact craters. That is remarkably few, and they are distributed almost randomly across the surface, with no heavily cratered ancient regions and no pristine young ones. Crater counts are how planetary scientists estimate surface ages. A surface with few craters is young. A surface with many is old. The numbers indicate that essentially the entire surface of Venus is somewhere between 300 and 700 million years old. That is deeply strange. The planet is 4.5 billion years old. somehow the record of its first 4 billion years has been erased. The leading explanation is that Venus, lacking plate tectonics to release heat steadily, instead builds up internal heat until it resurfaces itself in enormous volcanic episodes. Rather than venting continuously as Earth does, it may vent catastrophically every few 100 million years. And yet, there's more to this story, because it has not finished. For decades, it was unclear whether Venus is still volcanically active today. There were suggestive hints: variable sulfur dioxide in the atmosphere, unusually fresh-looking lava flows, warm spots detected in infrared, but nothing conclusive. Then, recently, a researcher went back to radar images collected in the early 1990s and compared observations of the same region taken 8 months apart. In the first image, it was roughly circular and covered about 2 square kilometers. Irregular in outline, and appeared to be filled to the rim. Nearby, deposits appeared that resembled a fresh lava flow. It was direct evidence of surface change on Venus, captured accidentally 30 years before anyone found it. Further reanalysis has since identified additional candidate flows in the archived data. So Venus is active. Volcanoes are erupting there now, resurfacing a planet whose entire visible history has already been overwritten once. There is something striking about that. The evidence had been sitting in an archive for 3 decades, waiting for someone to look at the right 2 images, side by side. The journey continues to what it took to land there. Between the 1960s and 80s, the Soviet space program mounted one of the most determined engineering campaigns in the history of exploration, and Venus was the target. The early attempts failed in instructive ways. Several probes were crushed on the way down because nobody yet appreciated how extreme the pressure was. Engineers kept rebuilding them stronger. In 1970, one finally survived. It transmitted for 23 minutes from the surface and became the first spacecraft to land successfully on another planet and send back data. 5 years later, another one returned the first photograph ever taken from the surface of another world. The image showed a flat landscape of angular rocks under a dim, hazy sky, with the horizon visible in the distance. After decades of imagining jungles and swamps, we finally saw the actual ground. The most capable landers came in 1982. They returned color images and analyzed the soil, and one carried a microphone that recorded the sound of wind moving across the surface. They were built like deep-sea submersibles with thick titanium shells and interiors pre-chilled before descent. They were designed to survive 32 minutes. One of them lasted 127. Every one of them eventually stopped. The heat gets in, the electronics fail, and the transmission ends. Fewer than a dozen images exist of the surface of Venus, and they were all taken more than 40 years ago. Now, let's go deeper, to somewhere on Venus that is genuinely pleasant. Not the surface, 55 kilometers above it. Atmospheric pressure decreases with altitude, and temperature falls with it. Climb high enough on Venus, and both drop to values that are, remarkably, close to Earth's. At around 50 to 60 kilometers, the pressure is roughly 1 atmosphere, the same as sea level here. The temperature is somewhere between about 0 and 70 degrees, depending on exact altitude. Aside from Earth itself, this is the most Earth-like environment in the entire solar system. There are complications, obviously. The air is unbreathable carbon dioxide, and the surroundings contain sulfuric acid droplets, which would attack most materials. But consider the engineering. Breathable air is lighter than carbon dioxide, which means that on Venus, a balloon filled with ordinary breathable atmosphere would float. A habitat there would not need a pressure hull, because inside and outside pressures already match. It would need acid-resistant materials, and that is largely a solved problem. There is also abundant sunlight, and the thick atmosphere below provides substantial shielding against radiation, considerably better protection than the surface of Mars offers. Concepts have been studied seriously for crewed airships drifting in that layer, riding the super-rotating winds around the planet every 4 days. Whether it will ever happen is another matter, but it is worth knowing, astronaut, that on the most hostile planet in the solar system, there is an altitude where you could stand on a platform in shirt sleeves, with only a breathing mask, and be comfortable. 55 kilometers below you, the ground would be hot enough to melt lead. But what happens when we ask whether anything lives up there? The question is not as unreasonable as it sounds. Those cloud layers have liquid droplets, moderate temperatures, sunlight, and available chemistry. On Earth, microbes are found in the atmosphere at high altitudes, so the idea of a purely airborne biosphere is not absurd. There is also a long-standing puzzle. Something in Venus's clouds absorbs ultraviolet light strongly, producing the dark streaks visible in ultraviolet images. Despite decades of work, the identity of that absorber has not been settled. Various sulfur compounds have been proposed, so, occasionally, have microbes. In 2020, a team announced they had detected phosphine in the clouds. On Earth, phosphine in that context is produced almost exclusively by biological activity, and no obvious non-biological source seemed adequate for Venus. The announcement attracted enormous attention. It also attracted immediate and vigorous scrutiny. Other groups reanalyzed the same data and found the signal was much weaker than reported, or consistent with a different molecule entirely, or absent. Independent observations produced conflicting results. The original team revised their estimate downward while maintaining that something was present. The honest summary is that the detection is not established. It may be real at a low level. It may be an artifact of difficult data processing. The clouds remain worth investigating regardless. But at present, there is no confirmed evidence of life on Venus, and the ultraviolet absorber remains unexplained. And yet, there's more to this story, and it concerns worlds far beyond this one. Venus matters enormously for the study of planets around other stars, and for an uncomfortable reason. When we detect an Earth-sized planet at roughly the right distance from its star, we tend to call it potentially habitable. But Venus is Earth-sized and sits at what many definitions would call the inner edge of the habitable zone. If an alien astronomer observed our solar system with instruments like ours, they would find two similar rocky planets in comparable orbits and have no easy way to tell which one had oceans. That is a serious problem, because it means an unknown fraction of the promising exoplanets in our catalogs may be Venus-like rather than Earth-like. Scorched, airless of water, and completely dead, while looking perfectly reasonable in a table of numbers. Researchers have begun mapping out a Venus zone, the range of orbits where a planet is likely to have undergone a runaway greenhouse. A meaningful number of known planets fall into it, which makes Venus far more than a local curiosity. It is our only close example of how an Earth-sized world in roughly the right place can fail. 3 new missions are being prepared for the 2030s. One will drop a probe through the atmosphere, sampling its chemistry all the way down and imaging the oldest terrain during descent. 2 others will map the surface with radar, far sharper than anything we have, searching for evidence of ancient water and current geological activity. After 40 years of near silence, we are going back. Take a quiet moment to reflect on what this means, astronaut. There is a way of telling this story that is frightening, and it is usually the way it gets told. 2 identical planets, one thriving, one destroyed by its own atmosphere. A warning delivered from 40 million kilometers away. I think that framing is too simple, and it misses something better. The truth is that Venus was dealt a slightly worse hand than we were. It sits closer to the Sun and receives nearly twice the sunlight. That difference alone may have been enough to decide everything before any question of what either planet did with its inheritance. What is genuinely remarkable is not that Venus failed, it is how narrow the difference was. Ours is not a robust, comfortable planet that was always going to work. It is a world that has been quietly running a chemical thermostat for 4 billion years, using rain, rock, and moving crust, and has kept itself within a livable band while the sun has grown steadily brighter throughout. The carbon that fills Venus's sky is present here too, nearly all of it. It is simply in the ground, held there by a slow cycle that has never stopped. That is not fragility, and it is not luck exactly. It is a system, and it has been working reliably for longer than anything else on this planet. Venus is what our chemistry looks like without the water to file it away, and Earth is what a very similar planet looks like when the filing keeps happening quietly for 4 billion years without anyone noticing. We drift away now, back through the acid clouds, up through that one comfortable layer at 55 kilometers, and out into the dark. Behind us, Venus becomes a smooth, pale disk again, blank and bright, giving nothing away. From here, it is simply beautiful, the brightest thing in the sky after the moon, exactly as it has looked to every person who has ever glanced west after sunset. Nothing down there will change tonight. The surface will stay at 465 degrees. The clouds will complete another lap of the planet in 4 days. Somewhere on those plains, slow, dense air will keep pushing gently at rocks that have not moved in centuries. And in the morning, if you are up early enough and the sky is clear, it will be there in the east. A single, steady point of light, holding all of that behind it. Close your eyes now. Let it go. Our own thermostat is still running, and it will still be running when you wake. Mission complete, astronaut. The stars will wait for you. Good night.